Hey, and this is part 4 of Introduction to Three-Phase Electric Circuits. In this particular presentation, we'll be looking at trying to solve three-phase power factor correction at unity, or for unity. Depends on how your grammar goes. So let's take a look. First, we'll do a quick reflection back on doing a power factor correction problem. In this particular problem, we had 80 ohms in series with 60 ohms inductive. And the first part of it is to find all the values for the RL circuit. So we isolate that out. And then since these two are in series, we would follow the procedure of finding your total impedance. Once you have your total impedance, you can get your current for that branch as well as the angle of the current. Find the individual powers for both the resistance and the inductance. We would then vector sum those two powers together to get our total apparent power. You could also get your total apparent power from ETIT, and you should end up with the same result. With our total apparent power in hand and our true power in hand, we can get our power factor. From there, we can go about finding an equivalent capacitive power to cancel out the inductive power. So to do that, we let QC equal QL, which in this case works out to be 345.3 vars inductive. We'll let that be the same. Having our total power in hand and knowing that the voltage across the capacitor is our source, we can then get the ohmic value for our capacitive reactance. With our ohmic value of our capacitive reactance in hand, we can work our way back and get our capacitance. At unity, the inductive side of our triangle has been eliminated. So all that's left is our true power. And that really is the definition of unity power factor. That means that your total apparent power, ST, is in unison with your total apparent power, PT. So at unity, ST is equal to PT, which we had calculated out earlier to be 460.8 watts. Now our source only has to supply enough current to feed the true power portion of the circuit, which in this case worked out to be 1.92 amps, and since it's purely resistive, it would now be at 0 degrees. So let's take a look at a three-phase circuit. Here we have a delta resistive network in parallel with a inductive reactive delta network. These two are in parallel, so we have to take a slightly different approach. We have to add the currents to get the total current. And again, we always use our line currents. If you don't remember how to do that, go back and take a look at the three-phase circuits part 3. Carrying on, your total line current will break up into both the line current feeding the resistive network, and the other portion will be the line current for the inductive portion of the circuit. We could then vector sum those two currents together, use the currents to find our angle for our total line current. We could then find our total apparent power from root 3 E line I line total. Again, where I line total is the vector sum of the line currents of the resistive and the inductive networks. You could find the individual powers and then vector sum the resistive power with the inductive power to get your apparent power. And with our true power in hand and our total apparent power, we could find our power factor. To verify our angle, we could take the arc cos of the power factor and make sure that that angle is the same as the arctan of our inductive current over our resistive current, again making sure that those are line values. We would then add a capacitive network to cancel out the inductive network. Now, since the capacitive network is connected in a Y and the inductive network is a delta, we just can't carry over the inductive ohms. We have to use the powers. Just as we did before, right? The current would cancel, the line current of the capacitance would cancel out the line current of the inductance. As we did before, we'd let QC equal QL, whatever that value is. But since the powers are the same, they have the same power, and they have the same voltage, then they would work out to have the exact same line current. And again, if you go back to the very first presentation we did on three-phase, line currents are independent of the shape. So we could just equally say that the line current in the capacitive network should be exactly the same as the line current in the inductive network for those two to cancel out. Using our phase current for our capacitive network, we could then calculate our capacitive reactance per phase. And make sure you use the phase current when you do that, and you use the phase voltage. Just as before, we had to find the phase current first because our ohmic values are always giving per phase. So make sure you use, when you calculate XC per phase, you use E phase over I phase, adjusting according to whether it's a delta or a Y, adjusting the current if it's a delta and adjusting the voltage if it's a Y. Once the capacitance cancels out the inductance, well then at unity, your total apparent power should equal your true power. At which point, at unity for one of these type of examples, our total line current will be equal to our total resistive line current, so that our source will only need to feed the resistive network. When the inductive network is charging, the capacitive network is discharging. And when the capacitive network is charging, the inductive network is discharging. And so you'll get a tank current between those two networks, and they'll feed each other once the system's up and running. So let's take a look at the solution for the network that we just had presented for us. Again, it's a delta connected 20 ohm resistive network in parallel with a 15 ohm inductive delta network. We will do a power factor correction using a Y-connected capacitive load. So starting off, we'll solve the RL network. We'll find our total line current, our power factor, and all our powers. So step one, we'll solve for the resistive network. Again, it's a delta resistive network, and what do we know about deltas? Well, E line and E phase are the same. So that means we can now calculate I phase, because E phase is 600 volts over 20 ohms per phase. That gives us 30 amps per phase. Now, knowing that it's a delta, we have to convert our phase current to a line current, where two phases will come together to give us a larger line. Since they're equal, we can use the multiplying factor of √3. And that gives us 51.96 amps. It's resistive, so it's at 0 degrees. With our line current in hand, we can calculate our total true power in watts. And in this case, it works out to be 54 kilowatts. Our next step is to solve for our inductive network. So that's step 2. Again, it's a delta connected inductive load. And again, it's a delta, so our phase voltage is the same as our 600 volt line voltage, which allows us to calculate the phase current in the delta, which works out to be 40 amps per phase for the inductive connected load. Again, we have to adjust our phase current to a line current, which means we have to multiply through by √3. This gives us a line current of 69.28 amps at a lagging 90 degrees. With our line current and our line voltage, we can calculate our total inductive reactive power for this network, and that works out to be 72 kVARs inductive. Now that we have the true power in our resistance and our inductive power and our two line currents, we can calculate the totals for that starting networks. Vectorally adding the resistive current and the inductive current gives us a total circuit line current before the capacitor of 86.6 amps at a lagging 53.13 degrees. That gives us a total apparent power of 90 kVAs at a 60% lagging power factor. And again, when we double check our power factor, that gets us back to 53.13 degrees. So we're safe in assuming that we're probably correct in our earlier calculations. Step 3 is to solve for unity power factor. And again, in order for it to be unity, ST is equal to PT, we have to get rid of our reactive power. Since our capacitive power is 180 degrees out of phase with our inductive power, we let QC equal QL, which is 72 kVARs. But since the power is the same, and we use, as an example, our reactive power is equal to √3 E line I line. And since it's the same power, 72 kVARs, with the same voltage, 600 volts, that means our inductive current and our capacitive line currents must also be the same. Because it's the same voltage, it's the same power, it must be the same current. So we can jump right to the statement where I line capacitance must equal I line inductance, which in this case was, as calculated out before, 69.28 amps. Our capacitance is connected in a Y configuration. And as we know from previous, line currents and phase currents are the same in Y connected loads. However, when it comes to a Y, our line current is 600 volts, but our phase voltage is less. So take your line, divide by √3, and that gives us about 346.4 volts per phase in our Y. Now that we have our phase current and our phase voltage, we can find our capacitance per phase, or capacitive reactance rather, per phase, which works out to be 5 ohms per phase capacitive. Now we can use our capacitance formula and work our way back, where C is equal to 1 over 2 pi f xc, and multiplying through, we end up with 530.5 microfarads per phase for each capacitor. At unity, now that we have our capacitance canceling out our inductance, at unity we're only left with our resistive network. So our new apparent power at unity is equal to our true power, which, as we calculated out at the start, was 54 kilowatts. Since our source now only has to supply the true power part of the network, then at unity, our I line total is now equal to the line current of the resistive network, which is 51.96 amps. So by correcting the power factor, our current went from, when it was an RL network, from 86.6 amps, now only has to supply 51.96 amps. And our source, back when it was an RL network, had to supply 90 kVA's worth of energy, and once corrected, now only has to supply 54 kilowatts worth of energy. This is the power of power factor correction. So let's do a quick recap. Three-phase power factor correction for unity. The general procedure is solve the original circuit. Solve your RL circuit, find all your powers. Once you get all your powers and all your currents, let your QL equal QC. Since it's the same power and the same voltage, you can let your capacitive line current equal your inductive line current. Once you have that line current for your capacitive network, all you have to do is adjust either the voltage, if it's a Y, or the current, if it's a delta, in order to get your phase values as you need them. Now you can solve for your capacitive reactance per phase. Once you have that, you can find your capacitance from your capacitive reactance per phase. Once your system is balanced, then at unity, your total line current is equal to your resistive line current. Also, once balanced, your total apparent power will simply be equal to your total resistive power. It's best practice that when you're doing your totals that you use your line values. That concludes this fourth presentation on power factor correction in three-phase networks. Thanks for watching.